Welcome to my online learning unit on perimeter, area and volume. Hopefully in this pack you'll gain ideas both on subject matter knowledge and pedagogical content knowledge of how to teach perimeter, area and volume. This chapter consists of various units such as the concept of perimeter, area measured in square units, how to find the perimeter and area of rectilinear 2D shapes, as well as surface area, volume, and investigating areas of parallelograms, triangles, and trapeziums. We'll then consider units and then the role of pi and circles, before moving finally on to research, a glossary, and then further reading so that you can enrich this part of your learning. So our first section is, what is the perimeter of a shape? By considering the perimeter is a length of the boundary around the edge of a two-dimensional shape. Learners usually learn this by, first of all, counting squares on grid, such as in this example. Learners will count squares inside, and as you can see here, I'm just annotating the inside, and this is mimicking what learners would normally do with counters or with other media. So here we have three rows of 5. Now then, because perimeter is a length, it is measured in units of length, such as centimeters or meters. This rectangle has two sides of length 3 units and 5 units, making this a 16 unit shape. Because 3 plus 3 plus 5 plus 5 equals 16 units. It's not difficult to generalize from a few examples like this and to formulate the rule that the perimeter of a rectangle with adjacent sides of length A units and B units is 2 times A plus B units. So we may generalize this shape is an example of what is sometimes called a rectilinear shape. In mathematics, this word is usually applied to a shape that is bounded by straight lines that meet at right angles. This means that a shape can be subdivided into rectangles, as shown in this second diagram. You can then use the fact that the opposite sides of any rectangle are equal to work out the lengths of the two sections of the perimeter that are not given, here labelled P and Q. In this simple example, P is clearly equal to 2 units and Q is 5 subtract 2 subtract 1 equals 2 units. The perimeter is therefore 5 plus 3 plus 2 plus 2 plus 2 plus 2 plus 1 plus 3, giving us 20 units. There are some excellent resources that you can use to teach and investigate perimeter. One of those is the geoboard, a readily available classroom manipulative, which consists of pegs on a board and elastic bands. As you can see in the diagram, this is a real geoboard that you can actually do, therefore giving learners concrete experiences and giving them the freedom to explore different shapes at their leisure. There are always digital resources as well. Here there is an online free geoboard app which you can download on iOS devices and Android devices, and this is available at the mathlearningcentre.org website, another excellent website for resources. So other resources, concrete examples of perimeter, you can use cards or very large manipulative cards and do practical exercises, as you can see here in this diagram. We can also measure the perimeter with a pedometer, as we see here, giving us the access to the outdoors, and outdoor learning is other manipulatives that we can use here are basic string and measuring, putting string around objects and then measuring the path around those objects, and then possibly laying the string linearly, and then using things like a small tape measure or a ruler or a meter stick to actually measure more accurately the length of string that was used to encompass the path around an object. Okay, so the pedagogy associated with the perimeter is the generalization that the perimeter of a rectangle with adjacent sides is 2 bracket a plus b units. It's a useful application of algebraic reasoning as well for older primary learners such as year 5 or year 6. And they can also be challenged to find the rule for the perimeter of a square, where the letter will be the same letter given that a square has equal length sides. You can also find the perimeter of a rectilinear shape through learning to divide it into rectangles, smaller units, and to work out the lengths of any sections of perimeter that are not given. This develops their reasoning skills and could be done in a collaborative, cross-curricular way. Our next section is what is area? So area is an amount of two-dimensional space inside a boundary. To put this another way, it is a measure of the amount of two-dimensional space covered by a two-dimensional shape. We have connotations here with and connections with multiplication arrays here also, but the units of measuring area are always square units. So for example here, the rectangle that I have here is 8 squares. As we can see, as we superimpose this, it is the rectangle covers 8 square units. If this was in centimeters, it would be 8 square centimeters, and it's a 2 centimeter by 4 centimeter array, which gives us 8 square centimeters, and this is abbreviated to 8 centimeters squared. This is an important point. We shouldn't really say 8 centimeter square. We should say 8 square centimeters, because 8 centimeter square can be misinterpreted as a square that is 8 centimeters long and tall, and obviously, as you can see, the area inside this square is 64 centimeters, so it's a different kind of an idea. So we must be careful how we say these answers. So 8 square centimeters is the thing. With obviously larger dimensions, a room, such as measuring the room. So classroom sizes should be measured in square meters with tape measures and measuring sticks, or even these days with digital tools such as Sphero or robots that have the ability to record their distance that they've measured. For even larger sizes and hypothetical cross-curricular measures, larger sizes should always be measured in square kilometers. And we can see that the proper way of writing that is kilometers squared. So the pedagogy with respects to of this section is to make sure that learners are aware that the rule for finding the area of a rectangle only applies to rectangles. So using the phrase area is length times width is a sloppy and wrong thing to say because other two-dimensional shapes have areas as well, but they are not found by applying this particular rule. Learners should also learn how to find the area of a rectilinear shape by dividing it into rectangles and subdividing it into smaller rectangles and finding the area of these before then adding these all up. Okay, so our next section is how to explain area and perimeter so that children do not get confused. Use the fields and fences idea to differentiate between area and perimeter. So the area is the size of the field, so the actual area covered by the field itself, and the perimeter is the amount of fencing around the edge. So we can distinguish between these two concepts in this way. It's a really good analogy, and it works in Wales because we are we not surrounded by fields and fences most of the time. They can then count up the number of units of fencing around the edge to determine a perimeter. So in this case, they could count the squares for the area, and we can then even count the number of fences. And what I'm doing now, as you can see, is a very common way for recording how children usually count the perimeter by be careful with the corners. So here we are measuring the actual measuring sticks themselves. So 1 square unit of area here is an unit of the area, and 1 unit of fencing, which is a line, is the unit of length. So in this example, we have starting from this corner here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the perimeter here is 18 centimeters long, and that is a length. The area, of course, would be a difference. It would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So here we have the area as being 16, apologies for that, centimeters squared, because that is the area encompassed by the shape. The pedagogy associated with this is to avoid confusion between area and perimeter. Use an illustration such as fields and fences to differentiate between these concepts and pose problems about area and perimeter in these terms. Area is the size of the field, and perimeter is the length of the fencing around the field. Okay, so our next section is what is the relationship between perimeter and area. And in general, there is and area. There is something of a surprise to many people because it's an interesting counterexample of the principle of conservation in measurement. For example, you can rearrange the fencing around the field into a different shape. The perimeter is conserved because the number of fences have remained the same, but the area that is enclosed is not conserved. This can change for any given perimeter. So for any given perimeter, there is a range of possible areas. This makes an interesting investigation, possibly for a geoboard or other squared paper for learners. Again, it's useful to couch the terms in fields and fences. So possibly the first challenge could be to find as many different fields as possible that can be enclosed within a given amount of fencing. So here we have a collection of shapes drawn on squared paper or diagrams. They all represent fields made up from rearranging 12 units of fencing. as I can illustrate here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you can see from the other shapes there, they're enclosing all of them are 12 units of fencing. They all have different areas, which is surprising to some learners, but this reinforces that there is no direct relationship between perimeter and area. An important discovery is that the largest area is always obtained with a square field or an arrangement which is as close as to a square as possible, and therefore this is the best use of a farmer's fencing material. So it could be used for a problem solving or a collaborative cross-curricular enrichment activity. If we were not restricted to the grid lines on squared paper, then the largest area would actually be provided by a circle. So imagine the fencing to be totally flexible and push it out as far as you can in all directions. We could actually enclose the maximum area. So the second challenge is the reverse problem, keeping the area fixed and find different perimeters. So in other words, what amounts of fencing would be required to enclose differently shaped fields with the same area? So here we have a collection of fields, as it were, all with the same area. They are all 16 square units. As the 16 square units are rearranged here to make the different shapes, the area is conserved, but the perimeter is not conserved. Once again, we find the squares to be the superior solution here, requiring the minimum amount of fencing for the given area. Again, another idea to try and problem solve a real life problem. If it's not possible actually to make a square, then using only the grid lines drawn on the squared paper, we still find that the shape that is nearest to a square gives the best solution. So the more general result, getting away from squared paper, is that the minimum perimeter for a given area is provided by a circle. It is interesting to note here that some ancient civilizations, land was priced by counting the number of paces around the boundary. So a shrewd operator in the ancient world in such an arrangement would make a good profit by buying large square pieces of land with a minimum perimeter and then selling these off as long thin strips which have a large perimeter. Okay, so the pedagogy here. So once learners understand clearly the distinction between perimeter and length, get them to investigate the way in which a fixed perimeter can produce a range of different areas, and vice versa. Consider using a geoboard for these kinds of activities. From other lectures, we have seen that the volume of an object is a measure of the amount of three-dimensional space it occupies. This is measured in cubic units. In this example, the cuboid, which is a solid shape with 6 rectangular faces, illustrated here, has a volume of 12 cubic units, made up of 2 layers, each of which is made up of 2 rows of 3 cubic units. This illustrates how the volume of a cuboid is the product of the height, the length, and the width. In this case, it is the 2 by 3 by 2, giving 12 cubic units. This result generalizes to the formula A times B times C, or A times B times C. This is the general formula for the volume of any cuboid with length A, width B, and height C. Solid volume can be measured in cubic centimeters. 1 cubic centimeter is the volume of a cube of side 1 centimeter, which is the standard units in base 10 materials. Larger volumes, such as the volume of classroom, might be measured in cubic meters. For example, a room 5 meters long, 5 meters wide, and 2.5 meters high has a volume of 5 multiplied by 4 multiplied by 2.5 would give 50 meters cubed. These ideas extend naturally to much smaller volumes measured in cubic millimeters. Finding the volumes of solids other than a cuboid, or a shape constructed from cuboids where learners can count the individual unit cubes, is beyond the curriculum for this age range. The surface area of a solid object is the sum of the areas of all its surfaces, measured in square units. The cuboid here has 4 surfaces with areas of 6 square units and 2 with areas of 4 square units, giving a total surface area of 32 square units. In this diagram, it illustrates another cuboid with the same volume, in other words 12 cubic units. The two cuboids can be made by arranging 12 unit cubes in different ways. Notice that although the volume is conserved when you do this, surprisingly the surface area is not. In the first, we see that the total surface area is 32 square units, but in the second cuboid it is 40 square units. This means that to cover the second one with paper, you would need 40 square units of paper, but to cover the original first one, you would only need 32 square units. This fact that rearranging the volume changes the surface area actually explains why you sometimes need less wrapping paper if you arrange the contents of your parcel in a different way. The closer you get to a cube, or more generally to a sphere, the smaller the surface area. Learners can be introduced to solid volume by rearranging various numbers of unit cubes. Here, the classroom multi-link cubes are essential in the shape of cuboids. You may choose to use numbers with plenty of factors so that the rearrangements can be more broad. Older, more able primary learners could investigate the way the surface area changes. Okay, so in this section we're going to look at how can we find areas of shapes other than rectangles. So, for example, the area of a right-angled triangle is easily found because it can be thought of as half of a rectangle, as shown in this diagram. In this diagram, the area of the rectangle is 6 times 4, which is 24 square units. So the area of the triangle is half of this, which is 12 square units. And this can be easily demonstrated by visualization, Bruner's pictorial representations and manipulatives such as this one. More able children might explore the areas of some other geometric shapes. So the teacher should be confident with the following material. For example, the area of a parallelogram, as is seen here, it can be found by multiplying its height by its length, or its base. This diagram here shows that this can be demonstrated rather nicely by transforming the parallelogram into a rectangle with the same height and the same base. For example, if we transform this, so if this parallelogram has height of 4 and a base of 3, then it has an area of 12 because we can superimpose the sides to transform it into a rectangle. This gives a way of finding the area of any triangle, really, just as in any right-angle triangle can be thought of as half of the rectangle. So if you make a copy, rotate it through 180 degrees, the two triangles can be fitted together to form a parallelogram with the same base and the same heights as the original triangle, such as in this picture here. Since the area of the parallelogram is the base multiplied by the height, the area of the triangle is half the product of its base and its height. For example, if the triangle has a height of 4 and the base of 3, it has an area of 4 times 3, which is 12, and half of this is 6. Again, note that any one of the sides of the triangle may be taken as the base. To a quadrilateral, such as this shape here, this is just one pair of sides that are parallel. So in the UK, this is called a trapezium. This particular trapezium has a height of 3 centimeters. So let me demonstrate. And the parallel sides have lengths of 4 and 6 centimeters respectively. The area of the trapezium can be found by cutting it into a parallelogram and a triangle, such as this. In this case, we produce a parallelogram with height 3 and base 4. So the area is 12. And the triangle of height 3 and base 2, because it will be the difference between 6 and 4, obviously. So the area of the trapezium is 12 plus 3, so it would be 12 plus 3. So the total area of this trapezium would be 15 square units. If it was in centimeters, it would be 15 centimeters squared. So this might be done in other ways, of course, and you should also consider exploring other ways of generalizing this approach and formulating a rule for the area yourself, and encourage learners to do the same. Learning and teaching points with regards to this section is some more able learners might explore areas of shapes such as parallelograms, triangles, trapeziums, hexagons, pentagons, of course, using the methods of cutting and rearranging triangles as exemplified in this section. But we could possibly also use software such as GeoGebra and also other manipulatives such as square bases. Okay, so this section is about relationships between units of area. So students, learners often get confused when changing between areas measured in square centimeters and square meters. This is because they fail to recognize that there are actually 10,000 square centimeters in every square meter. That does seem an awful lot, but doesn't it? But there are 100 centimeters. Remember that the square meter can be made from 100 rows of 100 centimeter squares, each with an area of 1 centimeter. So imagine using 4 meter rulers to make a square meter on the floor. You really would need 10,000 centimeter square tiles to fill this area. So an area of 1 square meter is 10,000 centimeter squared, and an area of 1 square centimeter is in effect 0.0001 of a meter. So converting areas between centimeters and meters squared involves shifting the digits 4 places in relation to the decimal point. For example, 12 centimeters squared, it would be 0.0012 meters squared, and half a meter, 0.5 meters squared, would be 5,000 centimeters squared. The potential for confusion here is even greater when converting between square millimeters and square meters. So take your time with this, but since there are 1 million square millimeters in every square meter, tread carefully and use visual manipulatives all the way through if possible. So in this section we'll look at the relationship between units of volume, which is slightly. When considering the cuboids, as in this diagram, you should note that the volume of a cuboid is measured in cubic units. And this is found by multiplying together the length, the width, and the height. Now a meter cube is 100 layers of 100 rows of 100 centimeter cubed. So 1 meter cubed, a cubic meter, must be equal to 1 million centimeter cubes. A million cubic centimeters. So converting volumes between centimeter cubes and meter cubes involves shifting the digits 6 places in relation to the decimal point. For example, 12 centimeter cubed would be roughly, or exactly more often, 0.0000012 of a meter cubed. If all these leads the reader to feel the need to brush up on their calculations with decimals, then they should do so with manipulatives. That's the issue of what is pi. But before I go on to explain what pi is and what it means for learners in primary mathematics, let me first of all begin by asking why do we use this letter? So this has an interesting kind of history, and it has connections with Anglesey in North Wales, and therefore has connections with Curriculum Cymraeg. So William Jones was a member of the Royal Society, and originally from Anglesey. He is a Welsh mathematician, well known in the area, and he is responsible for, in one of his books, for consolidating the use of the symbol pi to denote this constant in mathematics. So he's accredited with the use of the letter pi, and you can see here, as you can see in the lower diagram, his first use of the 3.14159 should be now denoted as equals to the symbol pi, and that universal use of this symbol now is attributed to William Jones. He was also friends with Isaac Newton and Edmund Halley, and as I say, a member of the Royal Society, and I think he was Vice Chancellor of the Royal Society at one point. So there's a little bit of trivia for you for that. So let us just consider the circle. So a circle is a shape consisting of all the points at a fixed distance from a given point. So the point is called the center, and a line from the center to any point on the circle is called the radius. A line from one point through the center to the opposite point on the circle is called a diameter. And the perimeter of a circle has a special name. The perimeter of a circle is called the circumference. So a point about terminology should be made here. So strictly speaking, the word circle refers to just the actual continuous line that makes up the set of points on the circumference. But in practice, we use this word loosely to refer to both the continuous line and actually the area or the space enclosed within. So this enables us to talk about the area of a circle, meaning strictly the area enclosed by a circle. We also know that we often use words such as radius, diameter, and circumference to mean not the actual lines themselves, but the lengths of these lines. So for example, we could say the radius is half the diameter, meaning the length of the radius is half the length of the diameter. One of the most amazing facts in all maths relates to circles. If you measure the circumference of a circle and divide it by the length of the diameter, you always get the same answer, which is pi, 3.14. It can be done in the classroom practically by using lots of different circular objects on a piece of paper between two blocks of wood. You could remove the object and mark the edges of the blocks on the paper, or you could measure the circumference. You could even cut out sponges and immerse them in paint and then trace wheel fashion. As the circle is turned, the paint leaves a trail, and you can measure that trail and directly then superimpose the diameter of that sponge on it, thereby for any size sponge you can visually show the relationship is always 3 and a bit. There are also circumferences also referred to in ancient civilizations and in the Bible. In Book of Kings 7:23, we read of construction. I quote: "A circular in shape, measuring 10 cubits from rim to rim, taking a line of 30 cubits to measure around it." So we can also measure pi more accurately, but it's a ratio, so it's important to be given a special symbol, so that's why it's given the symbol pi. And that concludes this section. We have the epilogue, and we have focus on research, glossary, and some further reading for you. I've collected some interesting research, so measuring in 2 dimensions. See a glossary of key terms and some explanations of these terms. And here we see some further reading. As you can see, tucker and cotton being some of the most recent, but obviously the work of Blincoln Slater and Fenner, especially the Fenner with the historical background to measurement of empirical and metric, is a comprehensive work and well. Okay, so if you have time, then a task for you to consolidate this knowledge would be to plan the simple maths lessons for year 5 in order to develop their skills in measuring area and perimeter. You may plan an instructional introduction, so some teaching at the beginning, but then move on to think of a thematic or cross-curricular activity that can challenge and help learners to progress their understanding of area and perimeter, and possibly incorporate some reasoning skills as well as oracy and writing skills. So if you could have a work on that, that would be great. So thank you very much for listening to this kind of online lesson. I hope this has been useful, and look forward to hearing for some feedback.